It was the ancient Greeks that developed the art and the science of geometry. They observed the shadows of objects, and by contemplating on how these shadows were formed, they developed the basic principles of projection and proportion. They noticed that a geometrical object, such as a triangle, throws a shadow image when illuminated. The distance between the light source, the object, and the screen determines the size of the image. The image can be made larger or smaller by changing the distance between the light source and the object, or the distance between the object and the screen. The shape of the image remains the same, only the size changes. By using such models, the ancient Greeks laid down the foundations of projective geometry. If two figures are identical in shape but not in size, they are said to be similar. If two figures are identical in shape and size, they are said to be congruent. This brings us to one of the most important and useful theorems in geometry. If two triangles are similar, their corresponding sides are proportional. The converse is also true. If two triangles have their corresponding sides proportional, then they are similar, or the same shape. Consider now any triangle ABC. Through any point D on AB, draw a straight line DE parallel to BC and intersecting AC in E. The triangles IDE and IBC are similar. Firstly, because angle IED equals angle ICB, these are corresponding angles, with IC as the transversal. Secondly, angle IDE equals angle IBC. These are corresponding angles with IB as the transversal. The angle at the vertex A is common to both triangles. Angle DIE equals angle BIC. The two triangles are equiangular, and this means they are the same shape, and in terms of geometry, they are similar. Now that we have established that the triangles are similar, we can assert that their corresponding sides are proportional. Corresponding sides means sides opposite the same angles. So in this case, the ratio of DE to BC is the same as the ratio of IE to AC, which is the same as ID to AB. This is one of the cornerstone theorems we have in geometry. It has many useful applications. We have here an example of a typical geometrical problem that we use in association with similar triangles. And here is the problem. In a triangle ABC, E divides AC in the ratio of 3:5. If we're given that BC is equal to 12 centimeters, find the length of DE parallel to BC. And here is a diagram which illustrates that example. We have a triangle ABC, DE is parallel to BC. We are given that BC is equal to 12 centimeters, and we wish to find the length of DE, which I denoted here by X. Now, looking at this triangle, you can see that IE to AC is 3:8, which implies from the given information. And in the triangles IDE and IBC, you can see firstly that the angle IDE is equal to the angle IBC, which I can mark here, angle IDE equals to the angle IBC. These are corresponding angles between a set of parallel lines. DE is parallel to BC, and it's being transversed by the line AB. Secondly, we can say that the angle IED is equal to the angle ICB, that this angle here is equal to that angle there, and they are also corresponding angles between the same set of parallel lines. DE is parallel to BC, but this time it's being transversed by the line AC. Thirdly, the angle A is common, which makes these two triangles equiangular, And if the triangles are equiangular, then we can say now that that implies, and this is the symbol we use for implies, the triangles ADE and ABC are similar, and therefore their corresponding sides are proportional. This enables us to write the ratio down, that is that DE is to BC. It must be the same as AE is to AC, and we already know that that ratio there is 3:8. Now we can substitute DE is equal to X is to BC, which we know is 12 centimeters, so X is 12, must be same as AE is to AC, which we know is 3:8. From this proportion, we can now evaluate X, which is equal to 12, multiplied by 3 and divided by 8. In this case, we can cancel 12 by 4 to give 3 and 8 by 4 to give 2, in which case we will get 3 by 3, which is 9 on 2. So that means that X is equal to 4.5 or 4.5 centimeters. And that's the answer to our problem, which enables us now to say that this length, DE, here must equal to 4.5 centimeters. Now this theorem that if triangles are similar, their corresponding sides are proportional, has many useful applications. Divide a given line segment AB into 3 equal parts. We can do this without a ruler, as the classical Greeks did, by similar triangles projection. We draw another line AZ at any arbitrary angle to AB and mark 3 equal lengths of arbitrary radius at C, D, and E. We then join EB and draw lines parallel to EB through D and C. We now have 3 similar triangles, ICC', IDD', and IEB, with their corresponding sides proportional. Although the unit measurement along IZ was arbitrary, as a consequence of similar triangles theorem, the points projected to IB divided precisely into 3 equal parts. And since IC to CD to DE are in the ratio of 1:1:1, therefore IC' to C''D' to D''B are also in the ratio of 1:1:1. If we draw another arbitrary line and choose another arbitrary radius, we will find that when the points are projected, they will intersect AB at the same points. Using this technique, we can divide any straight line into any number of parts. Thales of Miletus was the first person to state this theorem. If 2 triangles are similar, their corresponding sides are proportional. In his earlier travel to Egypt around 580 BC, he was fascinated with the Great Pyramid of Cheops. He asked the temple architects, "How tall is this pyramid?" And they said to him, "Oh, that's a divine secret. Only the god and the king knows the height of the Great Pyramid of Cheops." Thales said, "Rubbish." And with the aid of this theorem and the shadow from a vertical stick, he measured the height of the Great Pyramid of Cheops, and very accurately. He said it was 481 feet, and he was spot on. It was a sunny day. Thales put his stick in the ground upright and took 3 measurements: the length of the shadow of the pyramid, which included half the base, the length of the shadow of the stick, and the height of the stick. If we now look at the corresponding model, we have the pyramid with its shadow and vertical stick and its shadow comprising a pair of similar triangles. And here we have a diagram which depicts this situation. The big right-angle triangle here corresponds to the pyramid and its shadow, and the small right-angle triangle corresponds to the vertical stick and its shadow. Since the sun is very far away, we can regard these two lines, the hypotenuses of these two right-angle triangles, as parallel lines. If we now use h to denote the height of the pyramid and little h to denote the height of the stick, p to denote the shadow of the pyramid, and s the shadow of the stick, then we can write the ratio as follows. Since the two triangles are similar, their corresponding sides are proportional, so we have h is to p is the same as little h is to s. And from here we can find h equals p multiplied by little h and divided by s. And this expression here gives us the height of the pyramid.